Black holes explained. The science behind the cosmic giants black holes are among the most fascinating and mysterious objects in the universe. Their very existence challenges our understanding of space, time, and the laws of physics. Often portrayed in science fiction as voracious monsters that consume everything in their path, black holes are, in fact, incredibly complex cosmic entities that are not as straightforward as they might appear. The science behind black holes encompasses a variety of disciplines, from general relativity to quantum mechanics, and continues to captivate the curiosity of scientists and the general public alike. In this article, we will explore the science behind black holes, examining their formation, characteristics, and the fundamental physics that governs them. From their role in the evolution of galaxies to their potential links to the mysteries of dark matter and the nature of time itself, black holes remain a subject of intense scientific investigation. What is a black hole? A black hole is a region of space where the gravitational pull is so strong that nothing, not even light, can escape. The black in black hole refers to the absence of light and effect of the immense gravitational attraction within these cosmic giants. The boundary around a black hole, beyond which nothing can escape, is called the event horizon. The event horizon is one of the key features of a black hole, and it marks the point of no return. Once something crosses this threshold, whether it is light, matter, or radiation, it is inevitably drawn toward the singularity, the heart of the black hole, where the laws of physics as we know them break down. Formation of black holes. Black holes are formed from the remnants of massive stars. When a star runs out of fuel for nuclear fusion in its core, it can no longer support itself against the force of gravity. If the star is massive enough, at least 3 times the mass of the Sun, the core will collapse under its own weight, and the gravitational force will become so intense that it overpowers all other forces. This collapse leads to the creation of a black hole. The process of star collapse is a complex one. In stars smaller than about 8 times the mass of our Sun, they will likely end their lives as white dwarfs, small, dense remnants of the star. However, when a star of a larger mass reaches the end of its life, it will explode in a supernova, a dramatic event in which the outer layers of the star are ejected into space. The core left behind after this explosion can collapse into a black hole if the mass is sufficiently large. Types of black holes. There are several different types of black holes, categorized based on their mass, size, and other properties. Stellar mass black holes. These are the most common type of black holes, formed from the collapse of massive stars. Their mass typically ranges from a few times the mass of the Sun to several dozen solar masses. Stellar mass black holes are the ones most frequently observed in the universe. Supermassive black holes. These black holes are millions to billions of times more massive than the Sun. They are found at the centers of most large galaxies, including our Milky Way. The exact mechanism by which supermassive black holes form is still a topic of debate among scientists, but they are thought to be the result of the accumulation of mass over time, possibly through the merging of smaller black holes or the accretion of gas and dust from the surrounding galaxy. Intermediate mass black holes. These are black holes with masses between stellar mass and supermassive black holes, ranging from hundreds to thousands of solar masses. Their existence is more difficult to confirm due to their size, which makes them hard to detect. However, evidence for their presence is gradually increasing, and their formation could be an important piece of the puzzle in understanding how supermassive black holes came to be. Primordial black holes. These are hypothetical black holes that could have formed in the early universe, immediately after the Big Bang. They would be much smaller than stellar mass black holes and could have masses ranging from tiny to intermediate. Primordial black holes are a topic of ongoing research, as they could provide insights into the early conditions of the universe. Anatomy of a black hole. To understand how black holes work, it is essential to know the different components that make up a black hole. Although the specific properties of a black hole can be complex, they generally consist of the following parts. Singularity. The singularity is the center of a black hole, where the gravitational force is infinitely strong, and space-time curvature becomes infinite. The laws of physics as we know them cease to be applicable at this point. It is the region where all the mass of the black hole is concentrated. Event horizon. The event horizon is the boundary surrounding the singularity. It marks the point beyond which nothing, not even light, can escape the black hole's gravitational pull. Once an object crosses the event horizon, it is forever trapped inside the black hole, accretion disk. Many black holes are surrounded by an accretion disk, a swirling disk of gas and dust that orbits the black hole. As matter falls toward the black hole, it heats up due to friction and gravitational forces, emitting X-rays and other forms of radiation. This radiation is often detected by astronomers and helps them identify the presence of black holes. Relativistic jets. Some black holes, especially supermassive ones, produce powerful jets of particles that are ejected along the rotational axis of the black hole. These jets can extend millions of light years into space and are thought to be a result of the interaction between the black hole's magnetic field and the surrounding accretion disk. How do we detect black holes? Black holes, by definition, cannot be seen directly because no light can escape them. However, scientists have devised several methods to detect the presence of black holes by observing their effects on nearby matter. Gravitational lensing. The massive gravitational pull of a black hole can bend light around it, a phenomenon known as gravitational lensing. This effect allows astronomers to detect black holes by observing how they distort the light from stars or galaxies behind them. X-ray emissions. When matter from a companion star is pulled toward a black hole, it can form an accretion disk. As the gas in the disk heats up, it emits X-rays, which can be detected by telescopes in space. By observing these X-rays, scientists can identify the presence of a black hole. Gravitational waves. In recent years, the detection of gravitational waves ripples in spacetime caused by the acceleration of massive objects has provided a new way to observe black holes. When two black holes merge, they send out gravitational waves that can be detected by instruments like LIGO Laser Interferometer Gravitational Wave Observatory. Star orbits. In some cases, astronomers can observe stars orbiting around an invisible object with extremely high velocity. These stars' movements indicate the presence of a massive, unseen object, likely a black hole. The physics of black holes. Black holes are governed by the laws of general relativity and quantum mechanics. The general theory of relativity, proposed by Albert Einstein in 1915, provides a mathematical framework for understanding gravity as the curvature of spacetime caused by mass and energy. The equations of general relativity predict the existence of black holes, with their defining features of singularities and event horizons. However, the behavior of black holes near the singularity remains an area of active research. General relativity breaks down at the singularity, and a quantum theory of gravity, an as yet undeveloped theory that combines general relativity with quantum mechanics, is needed to fully understand the nature of black holes. Some physicists have proposed that quantum effects might resolve the singularity, but these ideas are still theoretical. The role of black holes in galaxy formation. Supermassive black holes, which reside at the centers of most galaxies, play a crucial role in the formation and evolution of galaxies. It is believed that these black holes form early in a galaxy's history and influence the galaxy's shape, size, and star formation activity. The powerful gravitational fields of supermassive black holes can strip material from nearby stars and gas clouds, fueling the black hole and affecting the dynamics of the entire galaxy. In some cases, the energy emitted by these black holes, in the form of relativistic jets and radiation, can inhibit or even halt the formation of new stars. Black holes and time travel. One of the most intriguing aspects of black holes is their potential connection to the concept of time travel. According to Einstein's theory of general relativity, black holes warp the fabric of space-time so intensely that time itself slows down near the event horizon. This time dilation effect has led some scientists to speculate that black holes could be used as gateways to travel through time. However, such ideas are highly speculative, and no evidence suggests that time travel is possible through black holes. Furthermore, the extreme conditions near a black hole would make it impossible for anything, let alone a human being, to survive the journey. The mystery of black hole information. A key issue in black hole research is the black hole information paradox. According to quantum mechanics, information about the state of a system should never be lost. However, when matter is consumed by a black hole, it seems to be lost forever, creating a paradox. This issue has led to many debates among physicists, with some proposing that information may be stored at the event horizon, a concept known as the holographic principle, while others suggest that information might be returned in a different form, perhaps through radiation emitted by the black hole. Resolving this paradox is one of the biggest challenges in modern theoretical physics. Conclusion: black holes are some of the most enigmatic and powerful objects in the universe. Despite the advances in our understanding of these cosmic giants, many mysteries remain, particularly at the intersection of general relativity and quantum mechanics. From their formation and structure to their role in galaxy evolution and their potential connection to the fabric of space-time, black holes continue to captivate the imagination of scientists and the public alike. As technology advances and new observational tools, such as gravitational wave detectors and more powerful telescopes, come online, we are likely to learn more about black holes and their fundamental role in the universe. Whether we will ever fully understand the mysteries that lie within these cosmic giants remains to be seen. But one thing is certain: black holes will continue to challenge our understanding of the cosmos for years to come.